So what we're going to look at is solutions, how we describe solutions, how we report their concentration in the units that we use for them, but also how we make a thing called a standard solution, which is what we did yesterday in class, is our wee experiment, because we need to have a standard to measure the concentration of other things against. So the first thing I'm going to go through with solutions is just a quick definition of what a solution is. Now the part of chemistry that we're looking at now, it's called volumetric analysis, so using the volumes of things and their concentrations to work out what they're made up of. So it means you have to know what a solution is. So a solution is a mixture that actually acts a lot like a pure substance. Alright, so it's where you have a solute, so a substance dissolved in a solvent, and it actually looks like it's a pure substance. You can't see bits floating in it or sitting at the bottom or anything like that. So, sorry. The key thing is that it's a mixture. Okay. The other key thing is that it acts a lot like a pure substance. So it acts like there's only one thing present. However, it is a mixture, so it does mean it can be separated. Okay, it means that I can actually remove things from it. It is made up of more than one type of thing, and in this case we're looking at what we call aqueous solutions, which are ones that have got water as their solvent. So it means that we need to know how much solute, stuff dissolved, is inside that solution. Because it's not a pure substance, it has actually got water as well as something dissolved in the water. So we need to be able to describe it. So we describe solutions using normally three different units in chemistry. You'll often see this on the bottles of products like vinegar, hair dyes, all sorts of things, alcoholic beverages of course, and you'll often see them something like this. Percentage, they might have V over V, or they might have percentage W over V, which is really bad science, but it's weight per volume when it should really be mass per volume. This is just volume per volume, so you'll often see this where the stuff dissolved as a liquid, like ethanol. So if it's beer or wine, you'll often see wine as something like 10% V over V. That means that 10 mils of every 100 mils, percent per 100, 10 mils of every 100 mils is ethanol. If it's a solid dissolved in there, you'll often see it as W over V. That would mean in every 100 mils of it, there are, for 10%, that would be 10 grams of it. For 1%, for every 100 mils, 1 gram of that is the solute. These ones are really useful in the real world, so we need to understand what they mean. Okay, they are closely related to another unit that is less useful in the real world, still useful actually, but more useful as a chemist, and that is grams per litre. Now these are basically grams per 100 mils, so it's easy to convert between these two units. If I knew that something was 10%, so 10 grams per 100 mils, how many grams is that per litre? If it was 10 grams in 100 mils, how many grams would be in a litre? 100. What did you do there? What easy maths did you do to turn it into grams per litre? Times it by 10. And it is that easy. So if I wanted to go from grams per litre to percentage, divide by 10. Awesome. Have confidence. We've got this. Okay? This unit is really, really useful in chemistry because we can use it to find amount. So little n. Okay, we can find amount. And what do we measure amount in? Moles. Good. Okay, so there must be another unit that has something to do with moles. Well, it's the number of moles dissolved in a certain volume. What would be a common sense volume to use? Mole per litre. Great. Now there's a relationship between these two. And this is why this is such a useful unit to use, because it's the link between the real world and the pure chemist's world. Pure chemists like moles per litre because we can work with mole ratios and stuff like that, and we can do the maths more easily with this one than we can with these two. But the real world likes percentages because we like to think that people understand percentages. I question that, but we like to think they do. All right, so I find it funny when something's described as 97% fat-free. They could also say this is 3% pure fat. Doesn't sound so good, does it? But we don't understand as consumers necessarily. Okay, so get off my soapbox. We can convert these units as well. Now, if I took away the per litres out of this, so this in a different colour, this is effectively what? If it was grams, what's that the unit for? What are grams the unit for in chemistry or physics? Mass. So it's effectively the mass. Okay? And moles is the unit for, we said this before, amount, which is little n. Is there a relationship between these two? Because the per litre is uniform. It hasn't changed, so we can ignore that for now. Is there a relationship you've met between mass and amount? What is it? Molar mass. Cool. So, if we remember, M equals N times MR. So if I wanted to find this value from this value, I times by MR. So guess what we do to go the other way?
Divide.
Brilliant. This little relationship here is one that's worth assigning to memory, okay? Because it is actually a really useful little relationship. I might leave the blue there actually. Okay, so what we did in our experiment is we were told we wanted a solution of a certain concentration. We were after our desired concentration or desired solution was 0.1 moles per litre of anhydrous sodium carbonate dissolved in 250 mils of water. Okay? So that's what we were after. And we had to work out how much to weigh out, then we had to dissolve it and so on. So I'm just going to quickly go through the maths again with you. It's not in camera shot, but everyone can see the maths I'm about to do on the right hand board as well, because I'm going to go a little bit more abbreviated here. We were also told, because it was on the container, that the molar mass of this stuff, whoops, get my formula right, was 106 grams per mole. It actually said 105.99, but we could only work with three significant figures, so we rounded it off to 106. We could even argue 106.0 if you wanted to go to 4. So we had that information. That's all we knew. We knew what we were after. We had scales so we could weigh out a mass. So we worked out how much we wanted to weigh out, and we found that we needed to weigh out 2.65 grams. We knew that because we could say, okay, the amount we required, knowing what we had there, so was equal to the concentration times the volume. Our desired concentration was 0.1, and our volume was 250 over 1,000. Why over 1,000?
Because there's so many are in a litre.
Fantastic. We had to convert our millilitres into litres. Okay, so I turned that into 0.250 litres. Cool. So that told us that we needed 0.0250 moles. Then I used my little relationship here between N, M and MR to find the mass. And I found that my mass was equal to 0.025 times 106, which was 2.65 grams. However, we saw that it was pretty hard to get exactly 2.65 grams for most of us. Some of us did very, very well and got 2.67 and so on. So then we had to work out the concentration of what we really made, because even though we were after 2.65, we had real difficulty, because of the size of the crystals, actually getting exactly 2.65 grams. So, and this is where we will need our calculators to help me with this, please. Changing colours again. We actually found that the mass that we used, I'm going to use the group that did have 2.65, 7 I mean. There was a group that did get 2.67 grams, okay, which is pretty awesome, but it's not going to be 0.100 moles per litre. I can tell that already. Okay, to three significant figures, it's not 0.100. To use this, which is what we call a standard solution, to use the standard solution, we need to know it to three significant figures. Otherwise, it's not a good enough standard solution. And you'll see it's very, very close to 0.100, but it's far enough off that we actually need to remember that. Okay, so now I've got my mass, and I know my molar mass. What can I find? The amount. Fantastic. So the amount I had is going to be 2.67 divided by 106.
0.025.
Keep going.
1886.
We'll go there. We'll go to four significant figures. Okay, don't round that off. That's excellent. Now I know the amount, and I know that it was 250 mils, because I'm confident that group filled their volumetric flask to exactly the right place with the bottom of the meniscus hitting the etched line. Okay. Now I've done that, I know my volume, I can find my concentration. My concentration is going to be this number divided by 0.025, divided by 0.25.
25.
So 0.02519 over 0.250.
0.1007547.
Okay, so 0.101 moles per litre if I round it off to the three significant figures. We don't go beyond the 3 for our final answer because our precision is limited to three significant figures if I look at all the equipment I've used through the experiment. The scales are only good to 2 decimal places, so three significant figures. 1, 2, 3. And although I've put 0.0 there, I shouldn't have, I'm sorry. The volumetric flask is 250 mils plus or minus 0.15 mils. So it's only correct to three significant figures. So my last answer can only be three significant figures. Okay, so just go through that again. My equipment limited me to three significant figures for my final answer. Okay, and that is an important thing in this, when we do the assessment, that your final answers are to the appropriate number of significant figures. Alright, just go through that process really quickly again. Solutions are a mixture that act like a pure substance. Because they are a mixture, we need to be able to describe how much of the solute is in the solvent, and we have 3 ways to do this. We need to know how to turn each of those units into each other, and it's quite good to put this thing that's in green and red into memory, so to know it off by heart. In an assessment, could I suggest that you write it down as the first thing you write, somewhere on the paper? Okay, that and the 2 triangles, NCV and NMM. Alright? When we make a solution, a standard solution, we can use that to find the concentration of other solutions, unknowns, which is what we're going to do for the next couple of lessons, actually probably for a week. To make that, we have to work out what we want, then we have to make it and see what we actually did make. So there's quite a bit of maths involved. And what I haven't put up here yet for you, which I will now, are the 2 triangles to also assign to heart. Okay, so knowing those as well. So basically here I've got stuff that you should write down on your assessment at the very start because we won't give it to you.